Hello, students. Welcome to the Electrical Engineering channel. So, in this lecture, I am going to discuss Simpson's 1 by 3 rule. And this lecture is a part of the course of numerical methods with MATLAB. In the previous lecture, we discussed analytical methods of integration, and we also discussed Riemann sums. So, this lecture is based on Simpson's rules for numerical integration. And the first rule is Simpson's 1 by 3 rule. So in Simpson's 1 by 3 rule, this is 1 by 3. The integrand is approximated by a second order polynomial. So as we all know that this numerical integration is actually done to evaluate definite integrals for complicated mathematical expressions. For complicated mathematical functions, the integration cannot be evaluated by simple analytical methods, which include integration by parts and integration by substitution. So, for those mathematical functions, numerical integration will be helpful. And we know that every complex mathematical function can be represented by a higher order polynomial. So, in Simpson's 1 by 3 rule, the function is approximated as a second order polynomial. So we will use f of x equal to a naught plus a1x plus a1x square, which is a second order polynomial. And in this polynomial, we have to evaluate these three coefficients, which are a naught, a1, and a2. So a naught plus a1x plus a2x square. And in this polynomial, we have three unknowns, right? A naught, a1, and a2. So first we have to evaluate the values of these three coefficients, and then we will be able to integrate this second order polynomial. So this second order polynomial is a simple function, and the integration of this polynomial is quite trivial. So by doing the integration of this polynomial, the numerical integration will become very simple. But the tricky part is the evaluation of these three coefficients. So for evaluating these three coefficients, we have to consider 3 points on the mathematical function, right? So first point will be considered as the lower limit of the integration, and the third point will be considered as the upper limit of the integration, and we will use one more point which is actually the midpoint of this interval from A to B. So first point, midpoint, and the last point of this integration interval will be used, and we will evaluate the values of the functions at these 3 points, and then we will use this equation. So at the end we will have three equations, and we have three unknowns. So by solving those three equations simultaneously, we will be able to evaluate the three unknown coefficients, right? So how will that be possible? So let's evaluate the function value at first point, which is a. So f of a will be equal to a naught plus a1a plus a1a square. Similarly, f of a plus b over 2, which is the midpoint of this interval, will be equal to a naught plus a1 into a plus b by 2 plus a1 into a plus b by 2 square. Similarly, the third equation will be constituted by using f of b equal to a naught plus a1b plus a1b plus a2b square, right? So these are the three equations, and by solving these three equations simultaneously, we can evaluate the values of a naught, a1, and a2. So the evaluation of these three coefficients by solving these three simultaneous equations is not that simple. If we uh, perform this derivation by hand, right, on the notebook, it will be very difficult, and the chance of error is very much high. So we can use MATLAB for this purpose. So if we use symbolic math toolbox of MATLAB software, we can perform the derivation by using MATLAB, and at the end we will just have the final expressions of these three coefficients. So how can this be done by using MATLAB? So this is the simple code, and we know that these are the variables which have to be used by solving these three simultaneous equations. So first variable is a, second variable is b, Third variable is f of a, then f of b, and f of a plus b over 2. So these are the five variables which are to be used in this derivation. So I define these variables by using this command. So sims a b f a f of a plus b over 2 is represented by this variable, and here we have f of b, right? So with these three equations can be represented in the matrix form. Okay, so how can we represent these three equations in the matrix form? I can show you. So here you can see these are the three equations which are actually formed, and these three equations can be represented in the matrix form. So our unknown variables are a naught, a1, and a2. So these are written in this column form, and this will be our matrix A, and that is the right hand side. So this is our A matrix, and this is our B column vector, and this will be our x. So ax is equal to b. So let's solve this set of equations by using MATLAB. Okay, this is our A matrix, this is our B column vector, and if we use a line solve AB command in MATLAB, we will get the values of A naught, A1, and A2. Then we will use the simplify x command, then we will display this, right? So let's run this code. Okay, now I am running this code, and after running this code, these are the values which I have obtained. So this is a1, this is a naught, this is a1, and this is a2, right? So we can compare these values by uh, what I have written over here. Okay, so this is, I think, quite simple if we do this using MATLAB. So these are our unknown coefficients, and now we have to evaluate the integration of this function. So integration of the second order polynomial is quite simple. So the integration of this function will be a naught x plus a1 x square by 2 plus a2 x cube by 3. So let's put the limits from a to b. So this is the final expression which will be obtained. And now we have to substitute the values of these three coefficients a naught, a1, and a2 in this integration expression, right? So put the values of a naught, a1, and a2 and do the simplification. Again, this simplification will not be too easy if we do this by our hand on a notebook. So we can again use the help of MATLAB, and the evaluated values of a naught, a1, and a2 will be substituted in this expression, and then MATLAB will give us the final answer. So let's run this code again, and now you have seen that these are the three unknowns, and this is the integration answer. So this integration answer is equal to b minus a divided by 6 into f of a plus 4 f of a plus b over 2 plus f of b. So this is the same expression which I have written over here, and this is the expression of Simpson's 1 by 3 rule integration if we have used two intervals, right? So we have used two intervals or two segments because we have used only the function values at 3 points: first point, last point, and the midpoint. So these 3 points will result two segment Simpson's 1 by 3 rule approximation. And let's solve an example, and after solving this example, the things will be clearer to us, right? So the distance covered by a rocket in meters from t is equal to 8 seconds to 30 seconds is given by x is equal to integral from 8 to 32,000 natural log 140,000 divided by 140,000 minus 2100 t minus 9.8 t dt. So let's apply Simpson's 1 by 3 rule, and Simpson's 1 by 3 rule states that x is equal to this expression, and we have the lower limit of a equal to b, a equal to 8, b equal to 30, and a plus b by 2 is equal to 19. So let's evaluate the value of the function at these 3 points. So this is f of 8, this is f of 30, and this is f of 19. Put these values in this expression, and this is what we have obtained at the end. So x will be equal to 11065.72. So now we can use multiple segment Simpson's 1 by 3 rule to get more accurate results, right? So if we have n number of segments, then our step size h will be equal to b minus a over n. So in this case, it was b minus a over 2 because we had two segments. For n segments, h will be equal to b minus a over n. And this integration will be equal to integration from x naught to xn f of x dx. So x naught is equal to a, xn is equal to b, and in between we will have several points. So this integration from a to b will be equal to integration from x naught to x to f of x. So this is the integration of first two segments. This is the next two segments and so on. And these are the last two segments. So we can use this expression which we have derived for two segments Simpson's 1 by 3 rule. And we can use this expression for all these sub integrations, right? And then we will add all those results and then we will have the final expression. So this expression of integration is equal to x naught minus x2 minus x naught divided by 6 into f of x naught plus 4 f of x1 plus f of x2. So this is first integration and this is the second integration, and this is equal to x4 minus x2 divided by 6 into f of x2 plus 4 f of x3 plus f of x4 plus so on, and this integration will be equal to xn minus 2 divided by 6 f of xn minus 2 plus 4 f of xn minus 1 plus f of xn. Now since this is our step size, right, h is equal to b minus a over n, and from here uh, b minus a will be equal to n times h, right? And if our n is equal to 2, then b minus a will be equal to 2h. Okay, so here again h is actually equal to b minus a divided by 2. So b minus a will be equal to 2h. So if we substitute the value of b minus a equal to 2h in this expression, it will become 2h over 6 or h over 3. So this will be actually h over 3. And here again, since we are using a two segment Simpson's 1 by 3 rule for each sub integration, so that's why here we will have h by 3. Again, here we will have h by 3, and here again we will have h by 3. So we can take that h by 3 as common or 2h by 6 as common, and we can add all these terms in the bracket. So it will be f of x naught plus 4 f of x1 plus f of x2 again plus f of x2. So it will be 2f of x2 plus 4f of x3 plus 2f of x4 plus so on. So such uh, summation will be obtained. So f of x naught plus 4f of x1 plus 2f of x2 plus so on up to f of xn. So it means for the first term, we will have a multiplier of 1. For the last term, we will have a multiplier of 1. And for the intermediate terms, we will have a multiplier of 4 if our I is odd, and we will have a multiplier of 2 if our I is even. So that is the final expression for multiple segment Simpson's 1 by 3 rule. And now we can solve the same example by using four segment Simpson's 1 by 3 rule. And for solving this, we have to consider n equal to 4. And let's apply that formulations over this example, right? So x is equal to h over 3 f of t naught plus 4 f I odd plus 2 into f of ti for I even plus f of tn. So h will be equal to b minus a over n, and n is equal to 4, so it will be equal to 5.5. A is equal to 8, b is equal to 30. So let's first evaluate f of t naught, which is f of 8, then f of t1, which is 8 plus 5.5, so it will be 13.5. Then f of t2 will be equal to f of 13.5 plus 5.5, so it will be 19. Then f of 24.5, it is actually ft3, and this will be our f of t4. So f of 30 will be f of t4, and it is equal to 901.67. So put these values in this expression, and x will be equal to 11 by 6, right? Because it was equal to h by 3. Okay, so h is equal to 5.5. So 5.5 over 3, or we can say that it is 11 by 6. So this is f of 8 plus this plus this. So at the end we will get the answer of 11061, right? So by mistake I have written 11067. So it is actually 11061. Okay, so I can verify this to you by, because I have done this summation by using MATLAB. Because here you can see 11 by 6, this is f of t naught plus 4f of t1 plus 2f of t2 plus 4f of t3 plus f of t4. So this answer is actually 11061.67. So this is 11061. So this summation of Simpson's rules can also be done by using MATLAB. So I have also written a code for it. So here you can see this is my a equal to 8, b equal to 30. For a two segment Simpson's 1 by 3 rule, n will be equal to 2. And this is my initial integration, which is initialized by 0. This is my function, which is the same function. And here I have used this modular condition, so it will evaluate modular division of I with 2. So if I is even, it will give me 0. If I is odd, it will give me 1. So if I is odd, then this condition will be true, and if I is even, this condition will be true. And according to this condition, my function will be multiplied by 2. Okay, so this is what we want to achieve over here. So you can see, if I have even I, then 2 will be multiplied in, and if I have odd I, then 4 will be multiplied. So that is what which is achieved over here. And then I will add my integration answer to f of a plus f of b. So f of a is the first term, f of b is the last term. The summation of these two terms is also added to the integration, and then I will multiply it by h by 3. So as well as I have done the exact definite integration of this expression for these limits, and then I will display both the answers. And let's run this code. Okay, so after running this code, you can see this is my Simpson's 1 by 3 rule answer, and this is the exact integration answer. And for two segment Simpson's 1 by 3 rule, you can see there is slight deviation between the two answers. Now, if I use four segment Simpson's 1 by 3 rule, then let's see what the answer I get. So here you can see my answers are become closer to the exact integration. So this is the exact answer, and this is the answer for four segment Simpson's 1 by 3 rule. Now, if I use my, if I divide my segments to more than 4, then my answer will become even closer to the exact answer, right? So that is what we have discussed in this lecture. So I hope you have understood the concept which are discussed in this lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.